Here we go. Synthesizing polysubstituted aromatic compounds. When we're looking at this, we have two things to think of. Number one, how the heck did we even put this on the benzene? What reagents did we need to use, in what order, to actually put these groups on? Secondly, how are these groups related to each other in their regiochemistry? Are they ortho-para to each other? Are they meta to each other? How can I guide these substituents to be in the right spot? So, let's take a look. First things first, how do we put these things on? That should always be your first step. First off, can you even remember how to put these things on? So, let's we'll go clockwise. Bromine, how do we put that on? Write it out yourself. Pause the video for all of these. See if you can remember how to put these things on. So, a bromine requires Br2 and a Lewis acid, iron or aluminum, and that'll go. Bromine's easy. How about that propyl group? How are we going to put that on? Pause it again and see if you can remember the reagents necessary. To put this thing on, we need to use our propyl chloride. 1, 2, 3, that's too many carbons, sorry. We need 3 carbons only. We need our Lewis acid. And we also need to go ahead and remove the carbonyl using the Clemmensen reduction. Later on, we'll learn a few other reductions, like the Wolff-Kishner reduction, or using thiols. We can do that as well. But for right now, we have Clemmensen. So that's how we put a propyl group on. Remember, can't use a Friedel-Crafts alkylation because that'll give you an isopropyl group. All right, last one is the alcohol in there. How are we going to put that on? That's the tricky one. And so, pause the video. All right, let's see if you remember. So, in order to put an alcohol on with the reactions we've learned so far, since we have not learned NAS yet, we have not learned nucleophilic aromatic substitution, we only know EAS. How we do that is we first put a nitro on there. We reduce it. Remember, the reduction is 2 steps. We're going to go ahead and turn it into a diazonium using sodium nitrite and HCl, and then finally we use acid. A lot of steps to put an OH on there, only using electrophilic aromatic substitution. And since this is a multi-step process, since both this and the propyl group were multi-step processes, we should also consider what their intermediates were. After step 1, we have a ketone for this, and then we'll have our alkyl group. After the first step, we have a nitro, an NO2. After this step, we have an NH2. After this step, we have a diazonium. So we can consider their effect on directing as well. Because maybe we need that OH to be a meta-director first, which maybe makes sense because we have 2 meta positions relative to it, but we have options. Always there's options. So let's look at everything we have here. So we really have at 5 different stages. Wait, 1, 2, 3, 4, 5. Oh gosh, okay. Then we of course have the OH. I should include the actual final ones, shouldn't I? So we have a ketone, a propyl group, an alcohol, a diazonium, an amine, a nitro, and a bromine. So that's 7 different things. So there are 7 different potential directors in there. So we want to think, how can we get these things to get in the right spots? First off, forget the bromine. The bromine is an ortho-para director. Both substituents are meta to the bromine. So bromine should probably be the last thing that we put on. because, at least of the substituents, of the last spots on the benzene, because the bromine will only be able to direct things orthopara. That said, if we want to look at what meta-directors we have, well, we have got a few. And again, there are options. We have meta-directors here. We have a nitro group, we have a diazonium group, and we have a ketone. All of these are meta-directors. And so we have our options. What do we want to do? Doesn't matter. Generally speaking, though, because we want our ring to react kind of most expediently, since we have our choice, basically ketone versus nitro, which to put on first. Both of those will direct the other substituents meta, which is fine. Again, it doesn't really matter on paper, but in the lab, you'll probably still want to put your best activator on first. And again, best is a relative term. So between the ketone and the nitro, ketone is slightly less bad, right? Ketone is a moderate deactivator, a nitro is a strong deactivator. So if we want our benzene to be the most reactive, let's put the strongest activator on first, which will be our ketone. So once we have that, on we go. Let's do our propyl chloride and aluminum chloride, and poof, we have, and because we know that's where we want it to be, I'm just going to install it there already. Makes it a little easier for us. We have our ketone now. This is not something we want in our final product, but we could always just do that later. We can use the zinc and mercury and HCl later. Who cares? We could take advantage of the fact that right now it is a meta-director. And so we have two options. We can put the bromine on, or we could put that nitro group on. Really, the biggest thing is determining what you can put onto the benzene. You can do all these other reactions later, converting the nitro to an amine. You can do that later, right? Once it's in that spot, it's only reacting in that spot. So the hardest part is actually getting things on in the right spots, and then you can work with them later. So, options. Put the nitro group on, put the bromine on. What happens if we do each? If we put the bromine on, we can no longer put the nitro on if we put the bromine first. Because once we put the bromine on, the bromine as a weak deactivator is stronger in terms of activating than a moderate deactivator. Blows your mind, right? So the bromine now takes over, and so now it's going to be orthopara. So, nope, not what we want. No good. A lot of this is guess and check, by the way. Trial and error would be a better way of phrasing it. So try it out, see what's going to happen. And then at each step, take the time while you're learning this. Take the time to analyze what substituents do. Are these moderate deactivators, strong activators, moderate deactivators, whatever they are. Okay, so bromine is not going to work because bromine is a better directing group, or it's going to take over. And unfortunately, it's not going to guide us to the right spot for our third substituent. But if we go ahead and put the nitro group on there, both of these are meta-directors. And we're still going to now be able to put that bromine on after. So this looks like a good step. So let's go ahead and put that nitro on there. And again, we don't want to reduce our ketone right away because we still need it to direct meta. We don't want it to direct orthopara. So here we go. Doing this, we will end up with our nitro group on here. And again, because I know where I want it to be in the final product, I could have put it on the other meta position. Symmetrically, it doesn't matter. I can still get the final product, but it's just easier, right? If you already know kind of visually where you want it. Either meta position is fine. So now we have to think, okay, if we want that bromine in a meta position, both of these are meta directors. So let's go ahead and do it. Let's put the bromine on. So Here goes our bromine. And we have the basic structure set. At this point, it's a lot easier to handle because now all we have to do is all this other crap, all these other reactions. And thankfully, it does not matter, now that we have everything on there, what order we do them in. I say that with a caveat in mind that we'll go over later. But generally speaking, your reactions don't otherwise interfere with each other. Unless you have other of the same group on there, then we've got problems. Like if you need to put two amines on there, or an amine and a nitro, which is very hard to do, things can get messy. But since all of our groups are different, the rest of these 5 reactions left don't matter. We can do them in whatever order we want. So let's go ahead and make it into a propyl group. Let's take care of that one first. Why not? Let's do our zinc and mercury along with the HCl. That gets rid of our carbonyl. We now have a propyl group. Everything else stays the same. Now we can go ahead and reduce our amine. So throw the zinc back in there with some HCl or iron. Again, multiple options here. Choose your favorite. Nothing else changes. We can now turn this into, oh, I forgot we needed the NaOH here. We can now turn this into the diazonium using the sodium nitrate. This is why I had you memorize all these reactions, right? Because imagine being like, okay, what the heck? How do I go from a nitro to a diazonium, right? You probably still don't remember, but that's okay. We have time right now. At least we get the geometry right. And then finally we can use our acid, add a little bit of heat, and we will install our group on here. So, a lot of things went on here. And thankfully, we didn't have to really stop to think about the reagents necessary. We know them already. We've covered them all. But still, this video is 13 minutes so far. Most of the work for synthesis should be in determining the regiochemistry. Where are my positions relative to each other? Where should they end up? How do I get them there? That's the real challenge here. Once you know the reactions, they're simple. This reaction turns a carbonyl into an alkyl group. Hooray! This one turns a nitro into an amine. Hooray! At that point, it's just memorization, right? That's not something that's really thought-provoking. But the thought part is coming up with where these are. So, recap. What did we do first? We looked at the 3 positions and we asked ourselves, how do we put these on here? And then, with all those steps, we look at the intermediates that are going to be there. We saw in order to put that propyl group on, we first have to put a ketone on, and then we make it to a propyl. But that ketone gives us the opportunity to guide our other substituents to where they need to go. So don't forget your intermediates either. We had 5 different options here of what to do first. And we have to think, okay, if I put this on, where would the other things go? So it's a challenge. It's going to take time. Practice, practice, practice. I have dozens of molecules for you to try your hand at. And while all of them can be done with EAS, we will see that some of them will use nucleophilic aromatic substitution, which is a subject for a later video. Since this video is running long, in our next video, we're going to take a look at a few more special considerations. So normally you can do reactions in whatever order you want, in the presence of whatever functional groups you want, but there's a couple special considerations, and we'll cover those in the next video.